So we've talked a lot about potential, and I mentioned in an earlier video that what we read in our wall socket, so you've got this wall socket, and it's got that's at least in the United States. What we say that wall socket has 120 volts, okay? And so this electric potential becomes a very a usable value that we can apply. And so the plug in the wall is a source of constant potential. As you hook things into it, you can know that that's going to provide a solid potential and it won't change. Okay, so we say that's a source of potential. A battery is another source of potential. Your standard battery it's got a bump on one end and it's flat on the other. And most of our batteries are 1.5 volts. Your regular AA batteries or a AAA battery or a C-cell battery. And then you have some different batteries, like 9-volt batteries are kind of shaped like this. Kind of shaped like that. Those are 9 volts. And then your phone and most small electronic devices have lithium-ion batteries. And they're set up to have more so around 3.7 volts. Okay, so your lithium-ion or your small electronics. Your small electronics have 3.7 volts. And this one is about 120 volts. That's created from a generator, which we'll talk about later in the semester. These ones are from chemistry. And in an upper level physics course, I teach about where this voltage comes from the chemical reaction. Okay. In this class, we're just going to have to say, well, the voltage comes from the energy inside a chemical reaction that supplies this voltage. And so really what it is you imagine a battery sitting here. It's got some chemicals inside that are able to push a charge. Well, technically it goes to the other way. So we're going to pretend they're positive charges, even though they're truly electrons. It's going to push this positive charge from the negative to the top. And if you hook it up to something, let's say a light bulb, we'll say that's a light bulb, okay, then this charge gets pushed through that light bulb and comes back. Okay, so we're going to get into circuits later on. That's going to be one of the powerhouses of this discussion. But we have to get the basics of how it works. And so a battery uses chemical energy to give this charge potential energy that can then do work through a circuit. And so the battery itself has the charges in it, but it supplies through chemistry, it supplies a constant voltage, a constant potential between its ends. And so we often say, this will be a 1.5 volt battery or 3 volt battery or whatever. And the cool thing about it is you can create whatever voltage you want by sticking them end to end. And like I have some flashlights at home that you can stick 2 in or 3 in. And so when I look at if this is a potential, if I call this 0, that is 1.5 volts, then this one's going to be 3 volts because it's 1.5 volts bigger than the bottom of it, and the bottom of it was connected to this one, so they're at the same potential, and that was 1.5 volts bigger than this one. And so by stacking these in order, you can just create whatever voltage you want. That'll be in units of whatever the fundamental chemistry is inside one battery. Now lithium ions is a different chemistry and gives you a different voltage. Okay. Now I have a cordless drill at home. That's a 24 volt cordless drill, battery powered drill, and that is simply a bunch of lithium-ion batteries, small batteries that are hooked like this, so that you can create a larger voltage. All right, so the important thing, that's all some really cool applications, but the important thing is that they are constant voltage, a constant voltage source. So if I have a battery, even if it's almost dead, the chemistry of moving even one charge is the same chemistry. And so even when it's almost dead, it's still going to be 1.5 volts if it's a standard battery. Okay, so they're constant voltage no matter how much you use them up. And they become really powerful. So our plugs, our batteries, they become really powerful because then we can create digital devices that we know are going to be supplied with this constant voltage and therefore run our device constantly. Now, capacitors we've been talking about these parallel plate capacitors. Well, they're also a source of electrical energy. Okay, if I have a negative Q here and a positive Q here, and I hook them across a light bulb, here's my light bulb. If I hook that across the light bulb, well, guess what? There's a path now, and these electrons want to merge back with these bare nuclei, and they can go through that. And so this, the path attracts them, and that gives this an energy. There's a potential energy to move these charges. And so because of that, we have an ability to do work. Now the problem is as a little bit of this charge leaks off, okay, and goes to the other side, is suddenly the amount of charge on either side has gone down. Okay, it's gone down a little bit. And we know that the potential is proportional to the charge by the electric field. Okay, so if the gap is D, and we know that the electric field inside a capacitor is constant, but it's proportional to Q over epsilon naught A. Well, it's constant in terms of how much charge is on it, but now I'm letting the charge decrease. So the electric field is actually getting smaller as the charge is leaking. So it's true the electric field is constant uniform over a capacitor, but only as it's sitting there not hooked up to anything. Once I hook it up, suddenly the charge can change and decrease, and therefore the electric field decrease proportionally. Okay? So that means my potential is also decreasing. So this is a source of electrical energy, just like your wall socket and just like a battery is, but it's not constant potential. And so they're not as useful in that sense. But there's a big field of technology and engineering of trying to use capacitors because they're actually a lot more efficient than batteries. You can charge and recharge and recharge and recharge a capacitor a lot more than you can a battery, even a nice rechargeable battery. And they don't wear down. There's not chemistry happening. It's literally just trying to keep charges separated from each other and then let them back. And so there's a lot of industries trying to see, could you use capacitors to run cars? And for their efficiency's sake, that's desirable, but it's a lot harder to do because the potential is not constant. Okay, so one thing we're going to do is talk about capacitors, since they are a very powerful subject, and then we'll also talk about batteries, especially a little bit later on. But a capacitor, we define a capacitance, okay, C, is defined. That's what 3 lines here means, defined. So it's not equal to by some other measure. We're just defining it to be a measure of how much charge could a capacitor hold based on the potential across that capacitor. Okay, so that's our definition of capacitance. And we can see that that depends on just the geometry by looking at how the potential, we just saw the potential, I should put a delta D there. We just saw that the potential is EV and the electric field is Q, I got a D here, over epsilon naught A. So this Q over epsilon naught A is the field. Well, the Q's cancel, and rewriting that, flipping the denominator fraction, I get that the capacitance is equal to this constant of nature times the area of the capacitor times the gap of the capacitor. And what's really important about that is that that has nothing to do with actions, nothing to do with charge that can change, nothing to do with voltage. It is purely a product of the geometry of the device. And because of that, I can create capacitors by machining. I could choose the area of the plates, I can choose the gap, put it together, and I have defined a capacitance. And so this becomes a really powerful variable that allows me to know how the charge is going to move around once I hook it up to a voltage source. So this is really important to remember. That is the capacitance of a capacitor, and this specifically a parallel plate capacitor, which was what we'll focus on. but it's purely a function of geometry. So I can machine it, put it in a package, and give it to you. Okay.